Greetings, this is Chemistry with Nav. In this video we're going to take a look at the reactions of aldehydes and ketones. In the previous AS video we saw that the oxidation of primary alcohols produces aldehydes and the oxidation of secondary alcohols produces ketones. If you remember as well, tertiary alcohols are not easily oxidized. Well, an aldehyde contains a carbonyl group which is the C double bond O. But that C double bond O has to be at the end of a chain. So that means you'll have an R group attached to the carbon with a double bond O, and then the other bonding space is taken up with a hydrogen. So an aldehyde group will always be at the end of any chain. In a ketone though, you end up with an R group, your C double bond O, and then another R group, which could be the same or it could be different, which basically means that your carbonyl group is going to be in the middle of a chain somewhere. The main reactions that these undergo will be to do with the fact that the carbon double bond oxygen is polar due to the electronegativity of the oxygen. And there are two main things you need to look at. One is the reduction and the other is the reaction with Cn- ions, both of which occur by the same mechanism. And the reduction, which is the opposite process of the oxidation, would either use sodium borohydride with water or lithium aluminium hydride, also with water. But if you look at the oxidation numbers of the hydrogen in either of those, let's take the sodium borohydride, sodium would ordinarily be +1, the boron is going to be +3, it's in group 3, therefore each one of those hydrogens is going to be -1 because we need -4 overall from the 4 of them. But also when you looked at oxidation numbers, hopefully you were told that hydrides have a -1 oxidation number. So basically this is a source of hydride ions. And that is H-, and if it's H-, that means that it must have a lone pair available for bonding, making that hydride ion a nucleophile. So when we come back to the mechanism, we're looking to attack the delta positive carbon with that lone pair. And we get our cascade of electrons, and the double bond moves its electrons onto the oxygen. So now we have the two R groups as before. The oxygen has a negative and a lone pair on it, and we've actually got the extra hydrogen now in place in the middle of the chain. The reason why the water is present is that we somehow need to finish this off. And the water is also polar, and that oxygen has a lone pair, so we get a bit more electron movement in order to take that hydrogen away from the water. There's our two R groups, but now we have an OH and an H on that middle carbon, plus an OH- ion, which means that I've managed to turn my propanone into propan-2-ol. And if I had oxidized propan-2-ol, I would have originally made propanone. So that's not too surprising. The other reaction is the reaction of something like ethanol, but this time with Cn- ions. So this could come from HCN or more likely KCN, where the Cn- ions also attack, so the mechanism is the same. But now I have the O- with the lone pair up there. I have my H, and I have my C triple bond N, which is bonded on. I still have to have a molecule of water, a bit more electron movement. There's my original CH3 group. I now have an OH and a C triple bond N. and don't forget your OH minus ion to make everything balance. So now I've got on this, I've got a hydroxy group at position 2, and because there are 3 carbons, that's called propane nitrile. So always make sure you count the total number of carbons. So 1, 2, 3. So now I put those two together, and I have 2 hydroxy propane nitrile. So both of these mechanisms are nucleophilic addition reactions, and that's the main mechanism by which aldehydes and ketones are going to react. The last thing we need to know about this is the identification of aldehydes and ketones. Now, you may have seen already somewhere else that Tollens reagent is the typical reagent used to identify between aldehydes and ketones, and you get this silver mirror test to tell you that you have an aldehyde because the Ag+ ions from the silver nitrate and Tollens reagent have been reduced to silver solid, which means that the aldehyde that was present has been oxidized to the carboxylic acid. However, that doesn't tell you what the original aldehyde or the original ketone may have been. So this time we use Brady's reagent. Which is 2,4-dinitrophenylhydrazine, shortened to DNPH. And if you have a carbonyl, so that means an aldehyde or a ketone, then you get an orange precipitate formed. But if you have a carboxyl group, such as a carboxylic acid, then you get no precipitate. So immediately this rules out any carboxylic acid that you may have in your unknown substances. So if you've got an aldehyde or a ketone, you get this orange precipitate, and the identification part, if I can spell identification, is you filter off the orange precipitate, you test for the melting point, and you compare the melting point to data book values. That melting point will be unique to whatever aldehyde or ketone there was originally when you ran the test. So this actually gives you an identification. It doesn't just show you a functional group, it tells you which chemical you actually started with.